Hello and welcome to another episode of Slam TV. I'm Professor Roger Yang, and today we're going to learn about tests for independence. Luckily for you folks at home, we've got a very special guest for you. He's an independent stats guru. He's a middle child that's not a troublemaker or a troubled maker. He's Professor Jay Cho.
Thank you.
Hey Jay, how's it going?
Pretty good, how are you doing?
Not bad. So, anything new going on?
Actually, there is. I got a tattoo, my first one.
What? So hip and modern.
Yeah, I drink fancy coffee too. Don't you have a tattoo, Roger?
No, I don't have a tattoo. My parents are old school. They would kill me if I got a tattoo.
That's true. My parents weren't too happy when my little sister got a tattoo too.
Your little sister got a tattoo as well?
Yep. So I got one, my sister has one. My older brother, the eldest one in the family, he doesn't have one. I think because he's too conservative.
Conservative? Maybe he's responsible, Jay.
Wait, aren't you the eldest one in your family too?
I am. I'm not a troubled middle child. I'm responsible.
Wait, so you think I got a tattoo because I'm a middle child?
Yeah. You know, I wonder if whether you got a tattoo or not is independent of your birth order.
I don't know, because people get tattoos for various reasons, right? I don't know if like one's birth order affects the likelihood that you get a tattoo or not.
If only there was a statistical technique we could use to test the claim that whether you got a tattoo or not was independent of birth order.
Testing for independent. Ooh, I know. I learned it. I learned it in my hypothesis test investigator training program. Yeah, and this technique is called test for independence.
What exactly is a test for independence, Jay?
Well, you start with two sets of category, and you want to see if the result of one category affects the likelihood of the other set of categories.
Not sure I really understand what you mean. Maybe we could use an example to explain it?
Sure, why don't we go and gather some sample data, then we can go over the example with our viewers.
Okay. Collecting sample data sure is hard work.
I know, I'm exhausted.
Well, at least we have the sample data.
Okay.
Why don't we use this sample data to help students understand this test for independence?
Okay. This type of table is called a two-way frequency table or a contingency table.
Is it two-way because we have two sets of categories?
Yes. Along the top, we have one set of categories. Remember, we asked people their birth order? Different column represents different birth order, eldest, middle, and youngest.
And along the left, we have a different set of categories corresponding to whether they have a tattoo or not.
And each entry of this table counts the number of people who have the corresponding row and column characteristics.
So, which cell do you belong to, Jay?
Well, since I'm the middle child and now I have a tattoo, I'm one of those 24 people. How about you?
Since I'm the eldest and I don't have a tattoo, I'm one of those 80 people. So what does independence mean in this example, Jay?
Well, basically, we try to see if the column variables are independent of the row variables.
Oh, so we're basically checking whether birth order, eldest, middle child, or youngest, affects the likelihood of whether you got a tattoo or not.
Right. If there's no effect, then we can say the column variables and row variables are independent.
I see. What if it turns out that being a middle child increases your likelihood of getting a tattoo?
That means the column variables are dependent on row variable because getting tattoo or not depends on your birth order.
Ah, I see. Why don't we lead our viewers through an example of a test for independence?
Okay, great. First, we need a claim. What do you want the claim to be?
Why don't we test the following claim? Claim, whether you get a tattoo or not is independent of birth order. So what's our null hypothesis going to be, Jay? This doesn't seem to be a claim about the mean or proportion.
That's right. This is a different type of test. In a test for independence, our null hypothesis is always H naught. Row and column variables are independent.
Does that mean that our alternative hypothesis HA is the rows and columns are dependent?
Yes, because H naught and HA are opposite of each other. Now, which one do you think is the original claim?
In our case, the original claim is the null hypothesis, H naught. So what's the distribution for this type of hypothesis test, Jay?
Well, to do this type of hypothesis test, we need yet another distribution.
What? Another distribution?
Yes.
But we already have the binomial distribution, we got the normal distribution, we got the student t distribution. Now you want to invite someone else to the party?
Yes. However, she's quite different than all others.
Really? How is she different?
Well, let's get to know her better. Well, first thing you notice that she has some scoliosis, so she's not symmetric.
Oh, really? I have some scoliosis. My left shoulder is higher than my right one. One eye is also bigger than the other. What other differences are there?
You know how the normal distribution can have both positive and negative z-scores?
Yes, it seems like the chi-squared values are always positive.
Yes, she's always positive. You'll never hear her say anything negative.
Oh, that's great. I prefer positive environments. I don't want any negativity bringing me down. Anyways, are there any other differences?
Well, remember student t distribution, how we had different curves for different degrees of freedom?
Oh yeah, student t.
Exactly. We have a similar situation. Chi-square distribution, we also have different curves for different degrees of freedom.
So we have these three graphs here. Wow, they look pretty different. It seems that as the sample size increases, the graph looks more and more normal.
And that's actually the last property of chi-square distribution I wanted to mention. As the sample size increases, the chi-square distribution approaches the normal distribution.
This chi-square distribution seems pretty cool.
Yeah, it is, and it can be used a lot for different type of testing, like test for independence and goodness of fit test.
So what's our random variable going to be?
Well, before we talk about a random variable, we need to kind of go over some notations.
Okay, let's look at our notation. O stands for observed frequencies.
And E stands for expected frequencies.
I is going to equal to the number of rows we have in our table.
And J is going to equal to the number of columns that we have.
Well, there's a lot of notation going on here.
I know. Let's start with the observed. This is just sample data we are looking at originally.
Oh, you mean our table of 6 different values?
The values 13, 24, 17, 80, 54, and 63. These are different values that we have for O's. These are called observed frequency because we observed them from our sample.
Okay, what about E?
Remember, when we do hypothesis testing, we assume that the null hypothesis is true.
Oh yeah, our null hypothesis was that the rows and columns are independent.
And by looking at the row totals and column totals, we can calculate our expected frequencies, assuming that null hypothesis is true.
Can you show us with an example, Jay?
Sure, I can give you 6 examples. Here, we have all the expected frequencies listed in red. I use my calculator and the chi-square test to calculate these. Take a look at the middle tattoo cell, the cell that corresponds to my situation.
We observed 24 people had tattoos, but you're saying that we are only expecting 16.8 people to have tattoos. What we observed was somewhat higher than what we expected.
Yep. For the eldest with no tattoo cell, we expected 20 people, but actually only observed 13. Here, what we observed was somewhat lower than what we expected. Well, let's take a look at expected and observed frequencies. First, we're going to look at the difference between expected and observed frequency. We're going to square it to make it positive. Then we're going to normalize it by dividing by expected frequency. We'll do that for all the cells of the table. Then we're going to add them all up.
Oh, and what's the net effect of doing all of this?
Well, it's going to give you a number that tells you how different the observed and expected frequencies are.
Okay.
If the observed and expected frequencies are not that different, very close, then our test statistic is going to be very small.
Oh, but if our test statistic is very large, that means there's a big difference between our observed and expected, which basically means they're very different.
Exactly. That gives you evidence that we can reject the null hypothesis that our row variables and column variables are independent.
Oh, okay. I think I get it. Can you lead us through the calculation of how we actually calculate our specific test statistic as well as how you found those expected frequencies?
Sure, let's take a look at the calculator. Well, first you need to access the matrix menu by hitting the second button and then x to the -1 power button.
Okay, what's next?
Move the cursor over to edit and then hit enter.
Got it.
Now type in the numbers of rows, in our case 2, and the number of columns, for us is 3. Then just enter your observed values. Wow, it seems like we successfully enter our matrix into a calculator.
Yay!
Nice.
Now, how do we find our expected frequencies, our test statistic, and our p-value?
Well, that's a lot of information. We're going to use chi-square test function under the stat menu. We need to tell it which matrix has our observed frequencies and which matrix to dump the expected frequencies in.
Okay, cool. Let's hit the draw button instead of calculate. I want to see the p-value graph.
Nice. Well, it says our test statistic was 7.0877, and we got the p-value of 0.0289.
I noticed from the graph that this test is right-tailed.
That's right, Roger. Tests for independence are always right-tailed. So what's our decision going to be?
Well, if we assume the standard significance level of 0.05, then we should reject the null hypothesis, H0. Okay, so we have our decision, which was to reject H0. What about the conclusion?
Well, since H0, the null hypothesis, corresponds to the original claim in this case, we also reject the original claim.
I think you mean to say sample data suggests that we can reject the claim that whether or not you got a tattoo is independent of birth order.
That's exactly what I meant to say. Does this seem believable to you?
Yeah, it seems believable. I mean, it seems to me like younger siblings would be more likely to get a tattoo than their older siblings. But having said that, tattoos are pretty common these days, so... Hey, can I see your fancy new tattoo, Jay?
Sure.